All right. So good morning, everyone. I've just started recording. So just to remind you, in the last lecture, we discussed how you may break a given two connected graph into its three connected components, right? So we take a two vertex cut and then we consider each component union those two vertices, and we add an additional edge between those two vertices. So that's called a marked S component, where S is your two vertex cut. And you keep doing this recursively, and at the end, the leaves of the recursion tree that you will get are going to be three connected graphs, or they may be K3 with multiple edges, right? And the three connected graphs are called the three connected components of the original graph. Okay. So in the example we did, we got K4 and K33 as the three connected components of our graph. And apart from that, we got three copies of K3, some with multiple edges. Okay. And this is really useful because for many problems in graph theory, like planarity, you don't need to look at all the two connected graphs. You just need to look at the three connected graphs. So if you can answer questions about the three connected components of the graph, then you can also deduce facts about the original graph. Right? So to give you an example, a two connected graph is planar, whatever that means, if and only if its three connected components are all planar. Okay. And we will talk about planarity in the next module. So if you have already seen it, then that's good. But if you haven't, then we will be defining it in another week or so. Okay. The main point is that for many problems, you can reduce them to the study of three connected graphs. Right. That was the main point of last lecture. But now we also need to know how to solve problems for three connected graphs. So we need some tools to deal with three connected graphs. And that is the topic for today's lecture. We are going to look at generation theorems, or if you look at them in the reverse direction, then they are induction tools for three connected graphs. Okay, so let me start with an example. So yeah, so I'll just try to explain what this theorem looks like, and then we will go into the proofs. Okay. All right. So let us suppose we have this graph here. Okay. So this is a three connected graph. So I'm going to first look at the induction direction. So what we want to do is we want to obtain a smaller three connected graph from this graph. Okay, so let's call this graph G. So notice that in this graph, if you delete any edge, then you will get a vertex of degree 2 because every vertex has degree 3, right? So that graph will not be three connected, right? If the vertex has degree 2, then its two neighbors form a two vertex cut, right? So the minimum degree has to be 3, right? Good. So we can't remove an edge, but maybe we can do something else. Turns out there is another very natural operation that we can perform on this graph, and we might be able to maintain three connectivity. But we might not be able to maintain it. We will see. Okay. So this operation is called contraction of an edge. So let me start with this edge here, E1. Okay. So what is contraction of an edge? We are going to delete the edge, and then we are going to identify its two ends. Okay, so if the edge E1 has ends X and Y, so then G contract E1 means you first delete the edge E1. Here E1 is equal to XY. And then you identify X and Y if the edge is not a loop. If E1 is link. Link means not loop, right? So this operation is called contraction of an edge. Okay, so let's see what happens when we do it in this particular example. So in this example, one way to think about it is keep the whole graph as it is, except for the edge E1 and its ends. Okay, so let's just draw the remaining graph. So these four vertices are as they are. And now I'm going to squeeze this into a single vertex. And I'm going to throw away the edge E1. Okay. So this is my squeezed vertex, or is often called the contraction vertex. And now all edges that were going to X or to Y, they will all go to this contraction vertex. Okay. So this is the graph G1, which is G obtained by contracting the edge E1. Okay. Now G is a three connected graph. And it turns out in this particular case, G1 is also three connected. You can check that easily. So this is also three connected. Well, immediately you have the question, is this always the case? Can I just choose any edge and contract it? And am I going to get a three connected graph? Any guesses? What do you think? Is that true? Can you just choose any edge you like and contract it and get a three connected graph? Assuming the original graph was three connected. Okay, since there are no guesses, let me tell you, let's just try another possibility. If you observe this graph closely, this graph G, there are basically two kinds of edges. There are the two edges joining the two triangles, and then there are the six edges of the triangles. All other edges are one of these two types. So if you want to state that formally in graph theory, it's called, those are the, well, so for any two edges, you can map one edge to the other edge, except for these three edges and the six edges of the triangle. So they can map to each other, but they cannot be mapped to, you cannot map any of these three edges to the remaining, to any of the remaining six edges. Okay. But anyways, I'm not going to get into that. It should be fairly clear from this graph. It's a very symmetric graph. Shivam has a comment. If the formed graph after contraction is simple, can you expand on that, please? Oh, I see. So Shivam's guess is that if you do the contraction and then the resulting graph is simple, then it will be three connected. That is not true in general. However, it is going to be true in this particular example. And after the example, I'll give you an example to show you why that is not true in general. Okay. So that's a very good point. That's a good guess. But it, yeah, go ahead.
Sir?
Yeah. Yes, Biplab, go ahead. Yeah, you want to say something, Biplab? Okay, if not, then let's look at this graph G contract F1 and let's see what happens there. So in this case, I'm going to have a single vertex here and its neighbors are going to be, this guy is going to be its neighbor twice because of both of these edges going to that vertex. And then there is going to be these two edges. Notice that I'm not going to throw away the parallel edges. Okay. or if I end up with any loops, I will not throw them either. Okay, so this is the graph G contract F1, and this is clearly not 3 connected because you have a vertex that has only 2 neighbors. When you delete those 2, your graph disconnects. Okay, so in this particular case, you got a parallel edge and your graph is also not 3 connected. So you might be tempted to think that whenever the graph is simple, it will be 3 connected, otherwise it will not be 3 connected. Right? That's it's fair to think that way, although it's not true. Let me give you an example where you get a parallel edge, but the graph is still 3 connected. So take this graph. Again, it doesn't contradict what Shivam is saying, because he's saying that if it is simple, then it will be 3 connected. So think of an example for that. What I will show you is the converse of that it may not be simple and it may still be 3 connected. Okay, so I'm not really answering your question, but for that I'll have to think of the example a bit harder. Let me see. I want it to be simple, but I don't want it to be 3 connected. I think we might be able to get an example for that. Let me see. So I want the graph to not be 3 connected. So supposing this is my contraction. Okay, yeah. Okay, so here is an example of a graph G, where if you contract the edge E, the resulting graph is simple, but it is not 3 connected. Yeah. Okay, so it turns out that that's not a criterion for the resulting graph to be 3 connected. But anyways, we are not looking for a criterion right now. We will come back to that point later. The point here is that for some edges, when you contract the edge, you may be able to preserve 3 connectivity. For some other edges, you may not be able to preserve 3 connectivity. Okay, that's just how things are. But we will prove that unless your graph is really, really small, there is always an edge. There exists an edge such that when you contract that edge, the resulting graph will still be 3 connected. So Shivam has a comment that G is not 3 connected. That is true. That is true. G is not 3 connected. That's right. Okay. Sorry, bad example. Yes. So it's not 3 connected because I have these 2 vertex cuts. Okay. Okay, let me try to fix that. So let me put this edge here. Let me put this edge here. Now is this graph 3 connected? Does anybody see a 2 vertex cut in this graph? Oh, but now I get parallel edges. Okay. Good. Okay, so that's a good question. I don't know the answer to your question. So let's put this as a question. If supposing G is 3 connected and E is an edge, such that G contract E is simple, then is G contract E 3 connected? Okay, so that's a good question. Let's try to take this offline, because at this point I don't know how to create a counter example. Okay. If anyone sees a counterexample, please let us know, because it would be nice to prove something like this. If the graph is simple, does it necessarily mean that you will get a three connected graph? My guess is the answer is no, but I just cannot think of a counterexample right now. But I could be wrong. Okay, thanks. Good. All right, so coming back to our example here, we have an edge E1 such that when we contract it, we get a three connected graph as a result. Okay, now let's think about this graph here. What about this graph, G1? Can we find another such edge? Again, there are two types of edges. One type of edge is E2, the edges of the outside quadrilateral or four cycle. And then another type of edge is F2. So let's just draw both of these possibilities. So what happens if I contract E2? G2 is G1 contract E2. And in this case, I get this stuff, the upper triangle, and then I identify this into a single vertex. And then I will get two edges like this, and I will get this. Okay, so this is K4 with a multiple edge, and in particular that is three connected. In K4, between any two vertices, there are two internally disjoint paths. There are three internally disjoint paths. Okay, so this is three connected. And K4 is the smallest three connected graph. So if you remove one edge from here, then you will get the smallest three connected graph. Okay, and what happens if I contract F2? G2 contract F2, sorry, G1. G1 contract F2. So I will draw the remaining stuff like this. And then I will identify this into a single vertex. And what are the edges I have? Two edges go like this. And one edge goes this way. Right? Oh, I see. There are two edges on both sides. So these are parallel edges. Okay. And notice that this is again not three connected. You can delete these two vertices and the graph is disconnected. Okay. All right. But in each case, we were able to find an edge such that when you contract it, the resulting graph is three connected. And we were able to do this until we got to what is essentially the smallest three connected graph, K4 with multiple edges, right? Then you can delete those multiple edges and you can get to K4. Okay. So it turns out this is not a coincidence. And this brings us to the following theorem, which we will not be proving today. We will probably prove it in the next lecture. So this is, if I'm not mistaken, this is due to Thomassen. And let me just state it. So Carsten Thomassen is one of the most accomplished structural graph theorists who is currently alive. So you take any three connected graph of order 5 or more. Okay, so just not K4 or K4 with multiple edges, because those are the only three connected graphs on four vertices. Then Thomassen's result says that G has an edge E such that when you contract this edge, the resulting graph is three connected. Okay, so this is an induction tool for three connected graphs. And we will see an application of this result to prove the very famous Krotowski's theorem concerning planarity in the next module. So we will use this to prove Krotowski's theorem about planarity. in the next module of this course. Okay. Good. So I would like to prove this result, but just not today. Right now, I want to focus more on understanding this result and looking at it from a different viewpoint. So what this result is telling you is that you've got any three connected graph, you can find some edge, you can contract that edge and get a smaller three connected graph, right? I would now like to switch gears to thinking about the reverse of this. So how can you go from the small graph to the big graph, right? There must be a reverse operation of contraction. That was one of the questions asked, I think, in the very first lecture when I was trying to explain why we need to deal with multiple edges, and we discussed briefly about contraction of an edge, and someone asked what was the reverse of this operation, right? So let's look at that now. So if you already saw my the way I was thinking when I was constructing this incorrect example, you probably already saw what I was doing. I constructed the smaller graph first, and then I went in the reverse direction. I split a vertex into two vertices. I split this vertex into two vertices. And that is how I constructed this incorrect example, right? But that is actually the converse of contraction. So let's look at, okay. So how would I go back from, let's say, this graph, G1 to G? I would take this vertex and I would replace it by two vertices joined by an edge, right? And then I would have to distribute the neighbors or these edges which are incident at the vertex to those two new vertices that I created. Okay. And that brings us to vertex expansion. So it is, let me just say that it is essentially the opposite of contraction. I'm calling it essentially because I'm going to have to be more careful to make sure that the resulting graph is three connected. Contraction is unique. If I tell you to contract an edge, then the resulting graph is going to be unique, depending on which edge you choose, right? But this operation that we are going to discuss is not going to be unique. It's going to have some freedom in it. So that's why I'm calling it essentially the opposite. Anyways, it will become clear as we define it. So supposing G is any graph, although we only care to apply this to three connected graphs. And let's say V is a vertex of degree at least 4. V is a vertex of degree at least 4. Okay. Remember, all our graphs are loopless in this part of the course for three connected graphs. Okay. So I'm not going to worry about loops. So your drawing looks something like this. You have this graph G, and there is a vertex V that has at least degree at least 4. Okay. And some of these could be parallel edges. Okay. So what we are going to define is splitting this vertex. So we will replace this vertex by two vertices, V1 and V2. We will join them by an edge. And now all of the edges that were going to V, that were incident at V, will now be incident at either V1 or at V2. With the additional restriction that each of them should have at least two neighbors, apart from, let me say, three neighbors. Each of V1 and V2 should have at least three neighbors. Okay, so let me give you an example here. So I could make these two edges incident at V1, and I could make these three edges incident at V2. Okay, what I want is that each of them has at least three distinct neighbors in the resulting graph. Okay, so expanding the graph G at vertex V means delete V, or let's say replace V by two adjacent vertices V1 and V2, distribute all edges incident at V in the previous graph G to V1 and V2. So what I mean is that if they were adjacent incident at V, you now make them incident to one of V1 and V2. Okay, such that each of V1 and V2 has at least three neighbors in total in the new graph. Okay, notice that you have some freedom here. You have actually a lot of freedom here. If the vertex V was incident with 100 edges, you could split these 100 edges in many different ways. You could distribute them in many different ways between V1 and V2, right? The only restriction is that each of them has at least three neighbors in the resulting graph, which is a very natural restriction because we want our new graph to be three connected. So in particular, every vertex should have at least three neighbors, right? Otherwise, your graph is not going to be three connected. But think about it now in the reverse direction. If you want to go back from this new graph H to G, then what you would do is you would contract the edge E with ends V1 and V2. Note that G is exactly H contract E. Okay, and in this sense, the contraction operation is unique. When you contract an edge, you get a specific graph. But when you expand at a vertex, you have a lot of freedom. Okay, hopefully now this is a bit more clear. Okay, so it turns out that this vertex expansion operation is exactly the opposite of contraction when you are looking at this theorem. Okay. And what we will also prove is that whenever you take a three connected graph and you take a vertex of degree 4 or more and you expand the graph at that vertex, then the new graph you will get will always be three connected. Okay, so that's another theorem. I think, yeah, this one is essentially going to be do it yourself. It's not difficult at all. So theorem 9.12 is that you've got a three connected graph. Think of this as a converse of 9.10. And you take any vertex of degree 4 or more. Okay, then any graph obtained by expanding G at vertex V is also three connected. Okay, so yeah, so that is the definition, expanding G at vertex V, and the new graph, we call it H in this case. Okay, All right. So this one I want you to essentially prove it yourself, but I'll tell you one way to proceed. So if the graph H, let's say this is the graph H, if the graph H is complete up to multiple edges, so if H is complete, let me just use this notation complete star, which means the underlying simple graph is complete. Right. So whenever I say complete star, I mean that the underlying simple graph is complete. Otherwise, it's just too many words to write. If the graph is complete in the sense that any two vertices are adjacent, then it is clear. Then the statement holds. Why? Because your original graph is 3 connected. So the new graph is going to have at least 5 vertices. Okay, because you have a vertex of degree 4 or more. So you're going to have at least 5. Let me make this, let's see. Doesn't matter. Let me just add the assumption of order 4 or more, because I don't care about um, graphs like K3 with lots of multiple edges, because that could also be 3 connected. Okay, so your new graph has at least 5 vertices because you have expanded a vertex. Okay, and if it is complete, then it's going to be 3 connected because it's going to be K5, K6 or something, and you're going to have 3 paths between any two vertices, internally disjoint paths. So now you can assume that H has a pair of non-adjacent vertices. And if this is the case, then what you need to show is that H does not have a 2 vertex cut or a 1 vertex cut, which is easier to deal with. So what you now need to do is, supposing H has a 1 vertex cut or a 2 vertex cut, then you want to show that the original graph G must also have a 1 vertex cut or a 2 vertex cut. Okay, and that's quite easy because you have obtained H from G by just doing a small local modification. Okay, so argue that H does not have a 1 vertex cut, which is a cut vertex, or a 2 vertex cut. Okay, so it's really not difficult. Good. On the other hand, the converse 9.10 is trickier because here notice that there is a reason why this result is easier, because here you are taking any vertex and expanding it, and the result says that the resulting graph is going to be 3 connected. So it's true for any vertex of degree 4 or more. Whereas in theorem 9.10, you're saying that there exists an edge such that when you contract that edge, the resulting graph is 3 connected. Intuitively, it should be clear that such a result is going to be more difficult to prove because you have to find such an edge, right? Whereas here, it's about any vertex of degree 4 or more. All right? So hopefully, I've explained to you intuitively why one should be harder than the other. Okay? All right. Are there any questions or concerns at this point? Okay. If not, then I want to state some consequences of these two results. And I think that will be mostly all we will be able to cover today. Okay. So So one way to think about this result is that, let's see, how do I want to explain this? Okay. The way I like to think about it is I don't like to deal with multiple edges generally. One, because most of the problems in graph theory, multiple edges are not that relevant. Of course, that goes back to the question, why consider multiple edges at all? Notice that if you want to argue something about the original graph using the smaller graph, let's say you are trying to argue something about G using G1, okay? Then it's good to have all of the edges in place so that you can easily map edges, right? You can easily argue about edges in the original graph G by just looking at the edges in the graph G1. They differ in exactly one edge because we are not throwing away the multiple edges. Okay. So to retain those multiple edges can be quite useful when you're trying to argue about the original graph. Okay. Another point is that for many problems, as I said, multiple edges don't really matter. And in those cases, we might want a tool for simple three connected graphs. So we will be going there soon. Okay, I'll tell you about simple three connected graphs in maybe another 1 or 2 lectures. But right now we have multiple edges. So the way I like to think about it is I have a three connected graph. Let's say it is simple. I know that there is an edge I can contract and get a smaller three connected graph. Think of the original graph as a big graph. Okay. So I can contract an edge and get a smaller three connected graph. Now I may have multiple edges. So I like to throw them away and then again find an edge, contract it, and get a smaller three connected graph. Now, if you go in the reverse direction, what you need to do is whenever you do a contraction, you need to expand the vertex. But now you may have to add back those multiple edges that you threw away. So you also need the ability to add edges to the graph. You may add multiple edges, but it turns out that you can also just add any edge to a graph, and a three connected graph, if you add an edge to it, it will remain three connected. That is true for any value of k for k connectivity, right? If you add an edge, the connectivity is not going to go down, right? Think of the number of paths, right? So the number of paths is only going to remain the same or increase between any two vertices. So, okay, so one way to think about theorem 9.12 is that if you think about both of these results together, 9.10 and 9.12, then what it means is that if I give you any three connected graph, you can start from K4 and keep expanding vertices or adding edges and get your final three connected graph. Let me just write this down so that it's precise, and then you can think more about why these two results imply this. So first I want to state this corollary. A graph is three connected if and only if you can obtain it from K4 by adding edges and vertex expansions. And one way to write that is to make it very formal. There exists a sequence, and I want you to think a little bit about ear decompositions here. It's a bit similar, but yet quite different. I want you to think of ear decompositions. There exists a sequence G0, G1, G2 up to GR of three connected graphs such that the first graph in this sequence is K4. The last graph in this sequence is the graph you want to construct. And for all intermediate graphs, Gi plus 1, in fact, this also applies to the last graph, is obtained from gi either by adding an edge or by expanding gi at a vertex of degree 4 or more. And if you want to think about it in the reverse direction, so this is for all I 1 less than equal to I less than equal to R, right? Sorry, less than R. Okay, so in particular, G2 is obtained from G1, G3 is obtained from G2, and so on and so forth until the last one. And another way to think about this part, the last part here, is that G, if you want to go in the reverse direction, then it means that the previous graph is equal to the next graph and contract some edge or delete some edge. So either you're contracting an edge or you are deleting an edge. Okay, so these are two ways of stating the same thing. Either you contract an edge or delete an edge from the next graph in the sequence to get the smaller one, or you add an edge to the small graph, or you expand a vertex of degree 4 or more to get the next graph in the sequence, right? And is it clear why this is true? Is everybody convinced that the previous two theorems, which we haven't proved, one of them is do it yourself, and the other one we'll be doing in the next lecture. Is it clear that these two results imply the corollary that I have stated here? Notice that the reverse direction is implied by theorem 9.12 and the forward direction is implied by theorem 9.10. Okay. Are there any questions or concerns? Okay. All right. So the question, of course, arises, what good is this theorem for, or this corollary for? So as I said, we will be using theorem 9.10, Thomassen's result, to prove Krutowski's theorem in the next module. Okay. What else? The other thing I want to mention is that, so here we are dealing with all three connected graphs, right? Which in particular includes multiple or parallel edges, right? So one natural question that arises is, what if I don't want to deal with parallel edges at all? Maybe my problem does not care about parallel edges. Another reason is applying this corollary is useful, but it has a limitation. Because you have parallel edges, you have a lot more case analysis to do in certain problems. So because of parallel edges, I also call them multiple edges. So one needs to do more case analysis, or one has to be very careful when you're trying to prove some more difficult theorems using this corollary. When proving other theorems. So this will become more clear when you do the first writing assignment. You will see it for yourself. Okay. So then what people asked is, what if we don't want to deal with parallel edges? What if you always want to ensure that you get a simple three connected graph, right? So if your original graph is simple and three connected, if you delete an edge, the resulting graph will still be simple, right? So deletion of an edge is not a problem. It will not create multiple edges. The problem is contracting an edge. When you contract an edge, you might create multiple edges, right? And that is actually another very interesting result I want to cover. It will probably take us another 1 or 2 lectures to get there. So there is a result called TUTS wheel theorem coming soon. What it tells you that you can actually have the same corollary, except that now you can put all your graphs to be three connected and simple. What's the problem? You can't do it if you just start from K4. There are these graphs called wheels, which will not allow you to get such a result because they don't have any edge so that you can maintain the simple property of the graph. I'll give you a quick example. This is a wheel. Actually, we already saw a wheel before. Sorry. We already saw one wheel. This is a wheel. Notice that when we contracted one of the edges, we got a graph that is not three connected. And when we contracted the edge E2, we got a graph that is three connected, but it has multiple edges, right? And these are the only two types of edges in this graph. You can check that any other edge is one of these two possibilities. Either you get a graph that is not three connected and is isomorphic to this one, or you get a graph that is three connected but is not simple, and in particular it is isomorphic to this one. So this happens for all wheels. I will leave this as an exercise. Take any wheel, so it's a cycle of length at least 3, and you have a vertex which is joined to all other vertices. Based on assignment 2, we call this a universal vertex. So you have a universal vertex that joins to all vertices of the cycle, right? That's your whole graph. And in a wheel, observe that for any edge, okay, so this is a do it yourself. For any edge E, either G contract E is not three connected, or G contract E is three connected but not simple. And deleting an edge doesn't make any sense, because if you delete any edge in this graph, you will create vertices of degree 2 on the cycle. Okay, the cycle's vertices are all degree 3. So if you delete any edge, you will create a vertex of degree 2. So that means that you have to contract an edge if you want to get a smaller three connected graph. But if you do that, then your graph will not be simple. And TUTS wheel theorem says that you have exactly the same corollary for simple three connected graphs. The only difference is that here you have to allow to start from any wheel, including K4. Okay. So if you just make this small change, then you get TUTS wheel theorem, which is harder to prove, of course. But we will be proving it. And on assignment 2, you will, on assignment 1, on the writing assignment 1, you will be using TUTS wheel theorem to prove a very interesting result. Okay. Good. So anyways, that's all I want to say today. In the next lecture, we will be proving theorem 9.10, and that will give us the corollary that we discussed. Okay. And after that, we will move on to TUTS wheel theorem. But my goal today was to give you a sense of where we are heading. And hopefully I was able to do that somewhat well. Let's see. right? So I just wanted to make sure that you all know where we are going in the next 2-3 lectures. Okay. Any questions or concerns? Does subdivision affect 3 connectivity? Right, right, subdivision. Okay, so subdivision is actually a nice thing to bring up here. So what does subdividing an edge mean? We have already discussed this, right? Have you already discussed subdivision? Yes. When did we discuss it? I'm forgetting. Okay, we have already discussed subdivision. So if you have an edge, you can subdivide it like this. Right. What do you think? If you, right. So it affects 3 connect, right. We discussed it for 2 connectivity. So subdivision preserves 2 connectivity. Generally speaking, are there any exceptions? If you take any 2 connected graph and you subdivide, you will preserve 2 connectivity. That is true, right? There are no exceptions to that. Good. But it doesn't preserve 3 connectivity, right? Because the moment you subdivide an edge, you create a vertex of degree 2. All of the subdivision vertices are degree 2 vertices. And so you don't preserve 3 connectivity by subdivision. What is interesting, however, is that subdivision is a form of vertex expansion. It is similar to vertex expansion, except that you are not following the restriction. So what you can do is, if you are subdividing some edge, let's say you subdivide this edge. One way to think of subdivision is to expand this vertex and give all the edges to this guy and only one edge to this guy. The problem is it's not a vertex expansion because you need to give this guy at least 3 distinct neighbors. So in that sense, it is not really a vertex expansion. It is a weaker form of vertex expansion. But what is still true is that if you contract this edge, you will go back to this graph. So subdivision is related to contractions and vertex expansions, but it is a weaker operation than vertex expansion. And in particular, it does not preserve the 2 connectedness, the 3 connectedness property. Does that answer your question? Okay, thanks. Any other questions or concerns? Okay. So I'll stop recording now, but I'm still here for another 4 or 5 minutes in case you have any questions or concerns.